So I'm just going to maybe tune up some points here, and I'll be lucky to get down to example number 4. The value of a to the power of 1 over n exists if n is an odd integer. If n is an even integer, then a to the power of 1 over n exists only if a is positive. Now I want you to think about that for a minute. So if you need to press pause, by all means press pause. So now let us suppose now n is odd. So I'm going to make up a number, so a to the power of 1/3. Now when our denominator is an odd number, a will always exist. Now, for example, if I do -8, I do -8 to the power of 1/3, I can quickly change this to the radical form. What's the cube root of -8? Well, it's going to be -2. And same is true if it's positive. So positive 8 to the power of, I messed that up, didn't I? Positive 8 to the power of 1/3 can be written as positive 8, cube root of 8, and that is 2. So both of these answers, or both of these will yield positive, or will yield answers. Pardon me. I'll try to get my math going on this morning. However, if this n is a negative number, like say for instance a to the power of 1/2. Now, if let's switch this to the radical form. That would be the square root of a. Now, the square root of a, now let's make a negative, like consider -4. What is the square root of -4? Well, what two numbers multiply to give you -4? Well, it doesn't exist. And the same thing can be said for whenever n is even, so that our radicand can't be negative. Yet the square root of 4 is equal to 2. So let's read that question or the statement over again and see if that makes any sense now. The value of a to the power of 1 over n always exists, if n is an odd integer. If n is an even integer, then a to the power of 1 over n only exists when a is positive. Now, if you think ahead, the radicand has to be positive. Note. Good. Some examples. -27 to the power of 1/3. Can I do this? Well, yes, I can. What number multiplied to itself 3 times gives you -27? Well, that would be -3. Versus, so that illustrates the first part of the statement. The second part of the statement is illustrated by this. Now, if you notice, the denominator is an even, so that implies that we are going to be taking an even root. So this happens to be the square root. The square root of -16 does not exist. And the reason why it doesn't exist is that there is no two numbers that multiply together to give you -16. So I feel good about that. Now I am going to jump over into something that may not make any sense initially. But please stick with me. Did you know that a to the power of m over n? Now, notice what happened here. My denominator is n, and my numerator, I'm going to call it m. Did you know that this is, in fact, can be converted into radical form, that it's the nth root of a to the power of m? Or, if you wish, you could call it it's the nth root of a to the power of m. So that the denominator is still the indice on your root, and the numerator is the exponent of your radical or of your base. Both mean the same thing. And for example, now which one is it? I don't know, either or. So just to maybe help us along as we make our arguments more and more and more complicated, I could take a look at a to the power of m over n, and I could move that and treat it a to the power of m over n. I could treat that as a to the power of 1 over n times m. Now I'm going to decompose my numerator. And we all know that 3 over 2 can be thought up as 1/2 times 3. And that's exactly what I'm doing here, except I'm thinking of it as 1 over n times m. So I can decompose the radical. And that's good. So you can have your thought like that if you wish. Now, when you see this, you know that this would be however, one could also say that you could decompose this as a to the power of n times 1 over n, and this would be a to the power of m to the 1 over m, or alternatively, you could write it like this. Now, take a look at what I've stated above. I'm just going to highlight this in blue. That is true. Which way do you do? Well, typically speaking, this way is going to be the more important one of the two. Shall I demonstrate? Example number 3. 4 to the power of 3 over 2. I'm going to write as a radical and then evaluate. If I was to write it as a radical, I could choose one of two paths. I'm going to pick the blue path, and notice that the denominator is 2. So I'm going to say that would mean the square root of 2 all to the power of 3. Alternatively, you could have said 4 to the power of 3 square rooted. Now, both of these quantities will be the same. However, the top quantity is easier to navigate. So I'm going to evaluate what's in the brackets. The square root of 4 is 2. And then don't forget to the power of 3. 2 to the power of 3 is 8. In the bottom now, I'm going to evaluate. Well, the way that I wrote it is I'm going to write it as I'm going to evaluate my radicand first. So 4 to the power of 3, it so happens to be 64. Square root of 64 is 8. And notice these two results end up being okay. Now, I much prefer the first one, in where you isolate the radical first and then conduct the power. Whereas, because really what you're doing is you're making your radicand and the root a very small number, and then you're raising it to a large power. Easy to do. On the bottom, 4 to the power of 3 kind of gets big, and that's 64. I probably lost some of you there because 4 times 4 times 4 is 64. And then you're taking a square root of a large number. Now 64 is a relatively small number, but the square root of a large number is harder to do, so it's 8. For sure, the first path is much easier.